My name is Hailong Zhang from the Ohio State University. In this talk, I will introduce our work on differentially-private control flow node coverage for software usage analysis. First, let me introduce the problem and our motivation. Software are collecting numerous usage data from users. The main goal of the analysis of this usage data is to learn how frequently certain things of interest happen in the population of users. In the typical scenario, there is an existing software application developed by the software developers, and the same software application is deployed to many users. The application collects some data about the usage of the software at users. This data is then shared with the developers of the software by sending it to a remote analysis server. This data could be used for user behavior analysis, finding popular software features, discovering performance bottlenecks, and so on. A prominent example is mobile app analytics. Each user runs her own copy of the app. The app collects and sends the usage data of the user to the analysis server to generate statistics for the developers. Other studies have shown that mobile app analytics is pretty common in reality. Most of the popular apps are using such analysis, and the millions of users are actually subjected to such analysis. Clearly, usage data collection is useful for software developers, but it comes with the cost of possible releasing of users' sensitive data. As in mobile app analytics, the data are collected from each user in order to calculate the statistics at the server. This data could be obtained by data breaches, could be used by rogue employees, sold to other entities, and could be combined with other powerful big data and machine learning analysis to infer information about users that they may not want to share with others in the first place. People are becoming more and more concerned about sending individuals' data to the server. Then the question is, how can we do software usage analysis in a privacy-preserving manner with principled privacy protection and a privacy by design solution? In this work, we apply differential privacy to tackle this problem. The focus of our work is control flow graph node coverage analysis. Control flow graph, or a CFG, is a graph representation of the control flow during the execution of a program. The definition of nodes in the CFG depends on the interest of developers. A node could represent a statement, a basic block, a function or method, or a coarse-grained software component, and so on. In each control flow graph, there is a start node, denotes the start of every runtime execution. An example of the start node is the main function in a program. Each edge in the CFG shows the temporal relationship between nodes. For this specific control flow graph, edge A to B means that the execution of A could be immediately followed by the execution of B. The execution at each user covers a subset of nodes and edges in the control flow graph. In node coverage analysis, we are interested in collecting and aggregating the coverage of nodes from each user. For example, for this particular execution, we have nodes start, C, D, A, and B that are covered. This is a very basic representation of software usage. Our analysis goal is for each node in the control flow graph to find out the number of users who have executed it. This is a very simple and fundamental analysis. For example, it can be used to find what nodes are popular across all users. If we do not consider any privacy protection, at each user, the execution of the software will generate some coverage of the control flow graph describing the execution. The analysis server will aggregate all the coverage data from all users to compute the frequencies of all control flow graph nodes. These results can be used for summary statistics, machine learning models, synthetic datasets, and so on, and shared with the developers of the software. During the data collection, since there is no privacy protection at the user end, the raw coverage information of each user is accessible to adversaries. And sometimes the analysis server and the software developers themselves may be considered as adversaries. To avoid this release of users' usage data, we propose to apply local differential privacy to control flow graph node coverage analysis. Next, I will introduce the details of our solution. The node coverage of control flow graph can be represented by a coverage vector at each user. The coverage vector contains one bit for each CFG node, and the bit is 1 if its corresponding node is covered at runtime by the user. For the example shown earlier, we have coverage vector CI including 7 bits, corresponding to the 7 nodes in the control flow graph. And then we have bits for node start, A, B, C, and D that are set to 1, and the bits for E and F that are set to 0. The goal of our differential privacy protection is to leak no information about whether a particular node is covered or not at each user during data collection. To achieve this privacy protection, each user runs a local randomizer R on the actual coverage vector Ci and generates a noisy version of the vector R of Ci. And this noisy vector is then shared with external entities, such as software developers, that could be adversarial. The randomizer R ensures that anyone, by looking at the output of the randomizer, cannot tell with high probability whether the bit for any specific node is 1 or 0. For example, the bits for A in this coverage vector. More technically, to protect the coverage of any particular control flow graph node, V, we define the local randomizer R that guarantees the indistinguishability of any pair of coverage vectors that are neighbors with respect to this V. For the example of the Ci and Ci prime on this slide, this definition of R should ensure that if someone looked at the output of the randomizer, she cannot tell with high probability whether the bit for A is 0 or 1. And in turn, she cannot tell whether A is covered or not at runtime. Now the problem is, how do we define neighbors? Because of the structure of the control flow graph, we can infer that if some node is executed, some other nodes are also executed. And if some node is not executed, then some other nodes are also not executed. To better understand this point, let's look at the previous example. In this control flow graph, B can only be invoked when A is executed. If we want to protect the execution of A, we have to also consider B's execution. Otherwise, even if A's coverage is protected, by knowing that B is executed at runtime, we can infer that A is also executed. Thus, the randomizer should ensure the indistinguishability between Ci and Ci prime, where the bits for both A and B are set to 0. This relationship can be captured by the dominator tree of the local control flow graph. In a control flow graph, a node D dominates a node M if every path from the start node to M goes through D. Dominator tree is a standard representation of the domination relationship. For any node in the tree, the set of its ancestors is the set of its dominators. For example, in the dominator tree of the control flow graph from the previous example, we have B as a child node of A, since its execution depends on A. And we define the sensitivity of a node in the coverage vector to be exactly the number of nodes in the subdominated trees rooted at that node. For example, the sensitivity of A in the coverage vector Ci is 2 in this case, since we have 2 nodes, A and B, in the subdominated tree rooted at A. Essentially, this means that we have to set 2 bits for A and B to 0 in order to achieve meaningful privacy protection. To protect any node in the control flow graph, we need to consider the upper bound of all sensitivities from all users. Suppose we know this upper bound S, then we can define randomizer R to flip each bit in the coverage vector with probability 1 over 1 plus e to the epsilon divided by S. We have proved that this definition satisfies differential privacy. Each user runs the randomizer and sends the output R of Ci to the analysis server. The server will aggregate all the reports and conduct a post-processing step to generate estimates of node frequencies to compensate for the noise introduced by each local randomizer. As we can see, when the bound S increases, the amount of noise and the privacy protection will also increase. However, the accuracy of the frequency estimates will drop. Now the problem becomes, how do we select a proper upper bound? First, we propose the worst-case baseline approach. Suppose we have a straight line control flow graph, and the worst case bound would be the number of nodes minus 1. The minus 1 here is due to the start node, which is covered by any execution. We have also proposed to tighten the bound via restricted sensitivity by mapping each vector to a restricted domain of coverage vectors with lower sensitivity. To further improve the accuracy, we propose to relax the strength of indistinguishability of neighbors so that for nodes that are lower in the dominator tree, we have higher privacy protection. The details of these approaches are in the paper. Next, I will show the results of the experiments and the conclusions. To evaluate the proposed techniques, we use 15 popular Android applications. We perform coverage analysis for both GUI screen view graphs and call graphs. The nodes in the GUI screen view graph are GUI screens, and the nodes in the call graphs are methods or functions. Screen view graphs are typically small, including no more than 100 nodes. Call graphs are larger, with hundreds or even thousands of nodes. We simulate 1,000 users for each app, and we use mean error as a metric for the evaluation. It is defined as the average of sum of differences of the true and the estimated frequencies. We have also used several other metrics for evaluation, but I will not talk about them here. The experimental results show a fundamental trade-off between privacy and accuracy. The baseline approach provides the strongest privacy protection, but yields the worst accuracy. As we can see, the other two approaches have much better accuracy, especially using the relaxed indistinguishability provides the best accuracy. That is 10 times and 19 times less error compared to the baseline approach for the two types of graphs. And if we only consider higher frequency nodes, the accuracy is even better. To conclude, privacy is highly needed for software usage analysis. Differential privacy is an appealing and applicable tool. However, existing differential privacy techniques cannot be directly applied. Domain-specific knowledge is needed here, for example, dominators. The proposed approaches can achieve high accuracy with meaningful privacy protection. Thank you for your attention. If you have any questions, please let us know by email.